Good morning or good afternoon, everyone, depending on where you're calling us from. And welcome to today's webinar, Optimizing Coal-Fired Power Plants in Asia, Enhancing Efficiency and Flexibility for the Future. We are pleased to have with us today Hans Conrads, founder and Chief Executive Officer of Promicon GmbH, based in Barleben, Germany. Promicon provides digital online flow measurement systems for novel applications in thermal power and industrial measurement and control processes. My name is John Evans from Christian and Associates, an energy industry marketing firm and a sales and marketing partner for Promicon, and I will be moderating this webinar. Our topic today addresses drift-free gas monitoring, providing real-time and accurate gas flow measurement using Promicon's Beacon Air technology, essential for maintaining efficiency and reducing emissions. During the presentation, feel free to submit any questions that you may have by clicking the Ask a Question box at the bottom of your screen. We will address as many questions as time permits at the end of the session and provide email responses to any questions that we don't get to. And now, allow me to introduce our speaker and welcome Hans Conrads, CEO of Promicon. Hans received a master's degree in electrical engineering from the RWTH in Aachen, Germany, and subsequently founded Promicon. He has invented numerous measurement systems for the power, cement, and smelting industries, and today, these measurement systems are installed in hundreds of plants around the world. Hans is the author of numerous patents and many conference papers on process measurement of gas and solid material flows. Without further delay, I'll now turn the presentation over to our featured presenter, Hans Conrads. Hans.
Well, thank you very much for the kind introduction to this presentation. I'm very happy that you're all here today to listen to what I have to say for the optimization of power stations. Basically, what I will talk about today is the measurement of airflow in power stations and gas flow in power stations. Coal-fired boilers have one measurement, which I call most neglected measurement in the power industry, and that is the measurement of air and gas flow. And we will go into that in great detail today, and I will show you examples of typical problems and the solutions to these problems. First of all, a few words about my company. We started in 1995, so our company has been around for nearly 30 years in providing services to thermal process industries, such as power and others. We're located in the beautiful city of Magdeburg in Germany, and our main markets are power, cement, waste to energy, and the smelter industry business. Also, our systems are used widely for optimizing these processes, such as stabilizing PID control loops, stabilizing fan operation, stabilizing combustion. So we're really mainly used for stabilizing and optimizing thermal processes. And of course, what our products mainly help for is to reduce maintenance, increase availability, save energy. That's really the key target of what we're doing. So, as I mentioned, we are active in several industries, which is mainly power generation, waste to energy, steel plants, as well as cement making, but also in non-ferrous industries. You can find our equipment wherever you have hot gas, dusty gas, and large duct work. This is really where you find Promicon in this world. And there are not many alternatives if you want to measure in a stable, drift-free manner your process gas flows. This is what our main markets have looked like so far, our main projects, we have been doing a lot of work all over the world. Here you can see our main three markets in power stations, steel plants, as well as cement plants. So wherever you are, I guess we have a lot of people from Asia today, but also in other parts of the world. We are quite active and we'll be happy to help you with your plant. I would like to talk about our Mecon Air system. And this is all about digital, drift-free, vector airflow measurement. That's a long word, but I will explain what it's all about and why all these three things, digital, drift-free, as well as vector, are so important if you want to measure process gas. Let's first look at process gas. I mentioned it briefly. What is process gas? Process gas basically has three characteristics for us. Usually it is hot, it is dust-laden, so it has dust and contamination in it. And thirdly, it goes through fairly large ducts. That is because of course, of the temperature of the gas, which requires a large volume, but also of the big systems that usually produce process gas. And before we dive into exactly what it is in your power station that we measure, I would like to briefly go to the locations, which are usually neuralgic and, let's say, the typical candidates for better flow measurement. It starts with the pulverizer section. Your pulverizers only work if they have proper airflow. Without proper airflow, nothing works in a pulverizer. So you need to be able to dry the coal. You need to be able to push the coal out of the pulverizer. And for both, you need the correct airflow through the pulverizer. This is already one of the big Achilles heels or the big weak spots in a power station. The wrong airflow usually produces the first problems that you have with your combustion, whether it's particle size of your coal or its distribution into your coal pipes, or it's simply unstable mill operation because your mill filling level is not correct, all due to wrong airflow. And I will go through that in detail. Secondly, the combustion air that you have in your boiler, it's called secondary air, is a big issue. I would say 90% of the boilers on this planet Earth have wrong airflow measurement, especially to the mills and the burners. This is a huge problem, and mostly it goes undetected. Most boiler engineers in this world, they know that they have some problem with airflow, but it's not so easy to spot that problem. And we help people to spot this problem. If you give us a printout of some of your screenshots of your DCS system, we can easily make you a small analysis and tell you where your airflows indicated in your system are not plausible and most likely wrong. So this is really the first big approach. What goes into your boiler as airflow? Is it correct? Yes or no? Is the distribution of your airflow correct? Yes or no? So big question that we're going to touch upon. Then on the outlet side of your boiler, you can see the gas flow. Also a big thing. We have many boilers in this world that have unbalanced gas flow, which means the left-hand side ID fan runs at a different rating than the right-hand side. These differences may only be small. You may only have a few percent of difference, but this represents the total gas flow through your system, and hence a small difference between left and right has a big impact on your particulate emissions, on your energy usage of your fans. Remember, your fans are one of the biggest energy drains in your plant. So we're going to go all through that, and we're going to have a look at airflow. So the first question that we must ask ourselves is, why do you have such big problems with your process gas in your power station? Let's look at your process gas. your airflow to the boiler is mainly preheated air. So you are sucking fresh air into your system, and this fresh air is cold. It has basically ambient temperature, and it goes through a so-called air heater. So the air heater, or usually you have two air heaters, one on each side. This air heater is basically regenerative. So it is a rotary heater. You have a lot of metal plates that move through the hot gas. You can see here on this red arrow, which is usually going from top to bottom, going down. And then these plates, once they're heated up, they rotate into the fresh air stream and heat the stream up. That's how you shovel the energy from the boiler outlet to the boiler inlet side, like a carousel. But as these plates rotate, they shovel a lot of flue gas dust into your fresh air. So basically all preheated air that enters your plant is contaminated with ash. You have ash in your ductwork, and if I think about some Asian markets like India, where you have high ash content in your coal, you have a huge amount of ash that is transgressing from the flue gas side into your fresh air side. And there it causes a problem. What is the problem that it causes? Take a look at this traditional way of measuring airflow. You have an air duct, you have a venturi, and you have a DP transmitter, which is measuring the static pressure and the dynamic pressure. So you have a difference in pressure of 20 millibar, typical, for full flow. Now the problem is that this pressure is transmitted to the DP transmitter along an impulse line. So this is a small tube that can get congested with ash. So it is possible that, let's say, one impulse line gets blocked with ash. And this is very common. I would say if you have 50 measurements in your plant or 30, I would say 1/3 of them is now at this moment suffering from some sort of congestion with ash. And what this does is it changes the delta pressure across your DP transmitter. Now, you must think of one thing. If your power station is located at sea level, you're looking at 1,000 millibar of total atmospheric pressure. Your DP transmitter is only measuring the delta P between static and dynamic pressure, but it all floats on a constant barometric pressure of 1,033 millibar. So if you have a blocked pipe, what is the pressure on the other side? Right? You have a huge drift impact because of that. Your delta pressure will drift as your impulse lines are blocked. And this drift will cause a drift in your measurement value. Now, please pay a little bit more of your attention to one more feature, which is the controller. The DP transmitter goes into your control system, and the control system is adjusting your vanes in the duct to control the airflow. And this is very important because the airflow to each burner, to each mill, is a controlled value to a certain set point. It is impossible for your operators to see a drift in airflow easily. It's very tricky because all of your airflows will be controlled to set point, right? So even if your airflow is 20% wrong, the controller will control your dampers until your wrong DP transmitter is reaching set point. So what does it mean? Look at this. You have here two things that we have recorded. You have the DP transmitter measurement, which is the dark blue line. It is a little bit noisy. And then there is a cleaning point in the middle of this picture. And after that, the dark blue line is the noise is gone, basically. So what the operator sees is I have a low quality signal, but it's at the right level. It's at 25,000 norm cubic meters. And after cleaning, it's at the same level, but it's not noisy anymore. Now, in this picture, you also see a different line, which is the light blue line, and that's the air damper position. And that's the air damper of that very duct that we are measuring. And you see the air damper before and after cleaning has a different position. How can that be? You have the same flow indication, but the air damper changed position. And the only answer is that your DP measurement before cleaning must have been wrong. That's the proof of implausibility. Yeah? So you can definitely see that you had a drift in your DP measurement that you have cured by cleaning your DP measurement. You can see this in all sorts of power stations. This is an example of an Alstom boiler in Germany. You can see the red line again, DP measurement. You see all the noise before the cleaning point, which is about 2/3 to the right. And then below, you can see above, you can see the blue line. This is damper position. And again, here, easy to see, before and after cleaning, the red line has the same level, but the associated damper has a lower level. Yeah? Sometimes the damper drifts up, sometimes it drifts down, depending on which impulse leg has been blocked. So it's totally unpredictable whether your DP measurement drifts upwards or whether it drifts downwards. It drifts somewhere. And again, remember, your operator cannot see this. Your operator is only looking at the red line and he sees, okay, everything is fine. By the way, the yellow line you see on the bottom is the Promicon measurement that was installed parallel. And here the operator could see before and after the cleaning, the value has drifted down like the damper. So this is pretty much plausible. The Promicon system always runs with the damper, and it never has a different ratio to the damper. Another thing that you can see here, typical problem with a clogged DP transmitter, you have a typical swing of the result. Some impulse lines, if the clogging gets heavy enough, you're not only having a bias, but you're also having a time delay, and that time delay before the delta P reaches the delta P transmitter can be quite long. And that's because some of the impulse lines are quite long. Sometimes the delta P transmitter sits 20 meters away from the duct. And then, of course, you have a large air volume that needs to be compressed in order to transmit the pressure. And that means your delta P transmitter also gets a time delay, and therefore you get a swing, a resonance between the damper and your delta P transmitter. This is usually when the operator first notices that he has a delta P transmitter problem. Right? But long before that time, you already have a drift problem, and that goes undetected. All right. Now, last problem. I was talking about a vector measurement. I was talking vectors. Why is it so important to have a vector measurement? This is a manifold of a large Alstom or combustion engineering boiler, and this manifold splits a big airstream up into 5 levels. And what you can see here on these trajectories is that depending on the branch that you're looking at, you have different swirl of the air. The middle branch has no swirl. So basically, what you see, the air is coming out of the plane of your screen on the bottom, this dark blue rectangle. So it comes out of your screen, and then it turns upwards 90 degrees into the middle duct. No swirl. But the 2 ducts adjacent to that, you can see that the air has to turn upwards, but also sideways, and then in another dimension again. So if the air turns several dimensions, it wants to go in a straight line because air has inertia. But the ducting forces the air in different directions. So as a result, the air will start to swirl because that's the effect, the physical effect of the inertia and the turn of the air. So what's the result? In every duct that you have, you might have swirl, but you don't know it. And if you measure delta P, swirl would really affect your reading. So swirled airflows are not good for delta P. And our measurement is not sensitive to swirl. Our measurement, our digital measurement, measures the flows without the swirl, which is a huge advantage over any delta P measurement. So now that I have talked about problems for some time, let's go into the measurement and how to resolve these problems. As we remember, the problems were measurements are not drift stable, they drift away in delta P, and we see a huge amount of influence from swirl that can give you wrong readings. The measurement that we have on the market for, we've had it now on the market for at least 15 years, is an electrostatic measurement of gas velocity. The gas velocity is measured directly with our system. We don't use delta pressure to derive gas velocity, but we measure the gas velocity directly. How do we do that? Imagine that you have a duct. The duct is shown here as the blue lined object, blue duct walls. You can see the flow direction of the gas, and in that duct you have a sensor. Excuse me, a sensor with an antenna, and this antenna is sensing electrostatic charge in the duct. So, for example, if you have ash particles which are flowing by the sensor, the sum of the charged particles is not always zero. So sometimes you have a slightly positive charge going by. Sometimes you have a slightly negative charge going by. So you can have a more dense cloud or a more thin cloud. And as you can imagine, these clouds are rushing by your sensor with a high velocity, 20 meters per second, so 60, 70 kilometers an hour, so quite fast. Now, you have a succession of positive and negative charge. What happens on your antenna is just the opposite. The antenna will always have the opposite charge that goes by. It's called Coulomb's law. Many of you might know it. If you're an engineer, you might have heard of it. So if you have more charge going by, you have more opposite charge on our sensor. Now, the change of charge over time is current. So we measure a current that has a certain fingerprint over time. We call this time signature. And this is important because this time signature is unique at every second. Every second you have a different time signature. And the way that we're now measuring is basically that we're putting two sensors up and downstream of the flow, so in succession. So you have the first signal on sensor 1, you can see on the top, second signal on the sensor 2, and if you do a cross correlation, so if you look at the overlap of the two signals, then at a certain time shift you will see a maximum overlap. This is called the cross correlation maximum. You can see it on the bottom. This is for two Gaussian or bell curve signals. Now, if you do this with real signals, and you can see our boxes here, they all have two sensors, one box with a processor. If you do this with real signals, you can see the signals being generated at sensor 1 and sensor 2. And you can see here the signals are very similar because the sensors are only about 300 millimeters apart from each other. So they are very close. The typical flow pattern does not change between sensor 1 and sensor 2. It remains pretty much the same, so the signals are very similar. If you put these signals on top of each other, you can see the similarity. This is the similarity of the signals. But you can see, of course, they are time shifted because the sensors are located downstream of each other. So sensor 1 is upstream of sensor 2. Now, if you take these two signals and put them into a cross-correlation function, you can see the cross-correlation maximum. This is exactly the time shift where the overlap of both signals is maximum. Right? In this case, you have 52.1 milliseconds flight time between sensor 1 and sensor 2. And the rest, of course, is easy. You have the distance of the sensors, which you know. You divide the distance by the time, and you get meters per second. Right? You get a certain velocity. Now, if you know your barometric pressure around the station, for example, in Korea at sea level, it's about 1,000 millibar. In South Africa, in the Highveld, it might be 880 millibar. So you can use the barometric pressure And of course, you need the temperature of the gas. And then you can calculate the STP flow, the standardized temperature pressure flow of the gas. And that's it. It's a very simple way of measuring. And the effect is stunning. What I've ever told you before about drifting, this would be the typical delta P signal that you have to purge the signal to get the drift gone, make the drift go away. On the bottom, you can see the Promicon measurement, no drift over the lifetime of the system. Yeah, if you put one of our systems into your power station or your cement plant or whatever plant, you put it in and you will not see a drift over the lifetime of the system. The system can't drift because we are measuring digitally the time of flight between sensor 1 and sensor 2. That's the whole deal. So that's what we call digital drift-free. That means, can you imagine, you will have no instrumentation engineer running around the boiler trying to calibrate 20 or 30 systems. The instrumentation engineer can focus on other tasks, such as stabilizing combustion, checking other things. Most of the plants I know do not have an instrumentation engineer who is checking drifting signals all the time. But your DP measurements are drifting all the time. If you put our measurement in, that problem is gone from day one. I was talking also about the swirl and the vector measurement. Now, think about one thing for a minute. You have two sensors which reach into the duct. These sensors are mounted perpendicular or orthogonal to the longitudinal axis of your duct. So they are basically pointing at 90 degrees angle towards the axis of your duct. And this is the vector that we are measuring. Yeah? So imagine you have a flow at a point, which is this orange arrow, which is not perpendicular on our sensors. Well, in this case, the time of flight will be measured on the two sensors, but the distance that we assume in order to calculate the velocity is the vector that is perpendicular on the two sensors, and that's it. So any lateral flow will not be seen by the sensors. The sensors only see the flow in the direction of the duct. So if you, for example, give me an example, have a typical swirl problem. Yeah, that's the swirl coming through like this, swirl flow. So you have the air going in a swirl direction. You will only see the vector that's between the two. You will not see any impact of the swirl. This system has also been tested in stacks by the German technical organization TÜV, and they came up with the result that our measurement is the most accurate measurement they've ever tested because of this ineffectiveness of swirl on our measurement. Swirl does not affect us. And I know that from some of the installed systems around the world with delta pressure, they use what they call honeycombed flow straighteners in order to take the swirl out of the measurement. All these flow straighteners give you a pressure drop in your duct. It means that you use more fan power. All of that stuff we don't need. If we have an existing venturi, that's the ideal location. We just put our sensors into the venturi throat, and here's your perfect measurement. And you don't have to worry about anything else. Now, there's another feature that is very important for you to understand. And that other feature is about the ionization of your gas. In your power station, most of the time, your gas flow is dusty. So you have enough electric charge to mark your gas flow and make it possible to read it digitally with our electrostatic sensors. However, when you start the boiler up, or when you have cold air that you put into your pulverizer, or also when you run at very low load, the electrification of the gas is not very good. So then we don't see enough electric charge that we can sense and correlate in order to get a good gas flow. For this, Promicon have invented the range extender. What is a range extender? A range extender is basically a rod that is protruding into the duct, and it emits small amounts of ionized charge. But this is a little bit like a spray electrode in a precipitator. The only difference is that our charge emission is much, much, much smaller. It's just a very, very little charge emission. But if you do that, and the electric pulse is not periodic, but it's sort of certain function or certain non-periodic function, then it correlates the same way that other signals correlate in the duct. So you can see here the electric pulse, you can see the sensed current, and if you look at the cross-correlation here, that's a typical cross-correlation of a range extender signal. You can see the two signals on the top right, and then on the bottom right, you can see the associated cross-correlation function. Very sharp, very precise. The range extender has some of the some big advantages. It's not only expanding the range of dust levels that we can measure down to zero. So we can measure with zero dust, and we can measure with very high dust. It also expands the measurement range down to just a few meters per second, right? So if you put our measurement into a Venturi, at full load, the Venturi has, say, 40 meters per second, 45 meters per second. Our range extender starts at 3 meters per second, 2 meters per second, right? So you have a 20-to-1 turn-down ratio. Yeah? If you have a turn-down ratio of 4, which is accurate on a delta P transmitter, you are lucky. Delta P transmitters have a lousy turn-down ratio. But the turn-down ratio of this instrument is very high because we have a linear way of measurement at the time of flight. And with this range extender, only very small velocities are already detected accurately. Why is that important? You want to know, for example, the cooling air to your burners once you shut off burner rows. Just one thing. If your power station doesn't have a big load factor, let's say you're not producing much generation, not much power all the time. Let's say you have solar power, you have wind power. We have this all in Germany, so the load goes up and down and up and down. So many times you have to go on low load. You switch off burner rows. How can you ensure that your cooling air to your burners is correct? If you have a delta P measurement, there's a good chance you're running a risk. So what many people do is they have a backstop, or they drill a hole into the damper. So they always know that they have a minimum flow to the burners. But very often that means your cooling air flow to the burners is higher than you would actually know. So the total gas flow through your boiler is on the high side, especially on low load. And if this is not controlled correctly, you lose a lot of energy. We all know excess air means direct loss of energy. So it is very important to measure burners also in the cooling position, which is very often the case if you run low load. You can do this with our measurement very well because it's possible to measure very low flows all the time. So let's look at a couple of technical features. This is how a system looks like. We have a Mecon Air box, which you can see on the right-hand side. It contains the electronics, it contains the outputs, it contains the power supply. Power supply can be 24 volt AC, or it also can be 230, 120, wide range. Then you have the two sensors going into our box, which give us the raw signal that is computed in the box. You can hook up a temperature measurement as well if you would like to compensate for temperature. And you can also, of course, put in the range extender. For power station applications, we would always recommend the range extender. Why? Because you don't want to have a drop-off signal if you go very low flows, cooling position, whatever. Also, if you start up mills, we would always recommend a range extender for power stations. We have power stations where the system has been running for 10 years without dropping, without drifting. Imagine if you have cooling air, you have 5% of the airflow through your burner, you have a turn-down ratio of 20-1. How accurate do you believe your delta P transmitter is at that low rating? I tell you, it's showing you any random number. It's some low value, but you have no idea whether you are currently running 2 kilograms per second or whether you're running 6 kilograms per second. It's completely random. With our system and the range extender setup, you have a very good low range control. And of course on the high range as well. So this all is installed into your station. I'm not sure how it is in Asia, but in Europe, the combustion air is usually demands a certain safety classification. So it's very important that you have in Germany safety integrity levels on your systems. The airflow usually has to have a safety integrity level of 2, so it's SIL 2. We offer this system as a SIL 2 device, and I think that's the only digital flow measurement for airflow in the world that has been certified for SIL 2. So it's a very, also a very safe device to use, especially for boiler purge when you start up your boiler. Again, if you have low load factors and you have to take boilers out because of renewable energy, it's very important that your airflow and gas flow measurement is reliable and accurate, because you need to do many boiler startups and you need to run boiler at low load. And that is always an airflow issue. So what's the motivation to install our systems? I think I mentioned it all. You have basically delta P transmitters in your plant. We know many plants that are very desperate. Again, I can only tell you, if you give us your some screenshots of your DCS system, of the mill, and of the draft fan group, we can and also give us some trending. We can show to you how implausible your airflow measurement is in your plant. It's very easy to see that your airflow measurement is not working as it should. So I can only invite you to make contact with us, and we can even do that via the internet, via emails. You just send us the screens, we show you in 1 or 2 calculations. This can't be right, you must have a big problem. So second one is, of course, permanent cleaning of the delta P measurement. When we go to power, when I see power, I've seen hundreds of power stations in my life. When I go there, I ask them, how often do you maintain your airflow measurements? They usually say, well, we maintain our primary airflow measurement very well. And then I ask them, and what about your secondary airflow measurement? And the typical answer is, oh, secondary we don't do. It's okay. And you all know it's not okay. The secondary airflow measurement is the same problem as the primary airflow measurement. The only reason why people in the plant do the primary airflow measurement is you have maybe 5 or 6 or 4 primary airflow measurements to take care of. The secondary airflow measurements, you have 10 or 20. So it's simply, it's unsustainable. It's unsustainable to do all this cleaning and that's all gone once you shift over to a digital flow measurement. Then, of course, safety rules. So basically, the big motivation is to get a grip on your airflow management and your gas flow management through the boiler, which is a very neglected measurement. I think it's the most neglected measurement in a power station. Because the boiler somehow, the fire keeps burning, you still keep producing. It's not that with a delta P flow measurement, you have to shut off the boiler. You can still run it, but you are running far from the levels of accuracy and also efficiency that you could run the boiler at if you had better airflow measurements. Well, let me show you a couple of examples of what we have been doing. First one is a power station in Germany. This power station had a delta P device installed. You can see here the Venturi. And this is a brand, this fairly new Alstom station, 800 megawatts, ultra supercritical, a single air heater for an 800 megawatt boiler, and all the bells and whistles. Now, what they quickly found was that the secondary airflow was drifting. They had problems with mills, they had problems with burners. So they installed our system into the existing Venturi and switched over to our flow measurement for all the mills and all the secondary airflows. And that's basically how it looks like. The retrofit of our system in an existing plant is fairly simple. You have to put in a couple of holes, you put in adapter pieces, you put the sensors in a certain distance, you put in the range extender, and that's basically it. That's all you have to do, and then you're finished. And what you get is a digital correct flow to the boiler at all times. Another example is not an Alstom, but a Mitsubishi Hitachi boiler. You can see here an individual gas flow to a burner. Similar thing, they had Venturis, and then they put in the measurements. Here you can see the two sensors inside the Venturi, and also here individual measurements. We've done this with a lot of the modern new Mitsubishi boilers running in Europe. Big one in Maasvlakte, in Rotterdam, in Wilhelmshaven, in Datteln, in Walsum. We have 5, 6 new boilers in Germany that all use our measurement for all their gas flows. One thing I have not talked about, maybe just to finish this up, you have basically two sides of your boiler that are important for gas flow measurement. One is the inlet side, which is all primary airflows, secondary airflows, overfire airflows. That's the inlet side. And of course, why is it so important? You would like to have the right air staging across all burner decks for the secondary air. You would like to have the right overfire air in the overfire air ports, because if you don't have the right airflow, you don't have the right penetration depth of your OFAR, and OFAR is ineffective. And of course, most important, you would like to have the right airflow into your pulverizer, into your mills. If your airflow to your mills is wrong, everything else is wrong. You have the wrong particle size, you have the wrong co-flow distribution, you have basically the wrong bed depth of your coal in the mill. So which is also upsetting your mill and can make your mills unstable. You can even trip your mill if you have the wrong airflow. You all know that. That's why people usually look at the primary airflow first. But let me tell you, secondary airflow is causing you a lot of NOx problems, a lot of CO problems, unburned carbon problems, a lot of eyebrows on your burner mouth, flame impingement on the other side of the boiler. The list of problems is endless. So knowing your airflow is a very, very important thing to do. By the way, just to mention that, if you would like to measure your coal velocities to your burners, that's also something that we can do. We're one of the few companies in the world that can also measure the dirty airflow after your mill into your burner. So you can see the right impulse of airflow into your burner. And it's even possible to measure the coal mass flow to your burner. So you can have a very good indication online of how the coal distribution to each burner is. So that's the inlet side of the boiler. But what about the outlet side? Is it once the gas is through the boiler, everybody's happy that it's over, and it goes through, and then it goes through the ID fan and then into the stack. Are there any issues? Are there any issues that you can find on the outlet side of your boiler? Well, what we've been finding many times in many installations is that the gas flow, the total gas flow through the boiler is not correct. And needless to say, very often it's on the high side, and that's exactly what you don't want. You don't want to have gas flow on the high side. Why? If you have gas flow that's too high, you have too much energy that you put out the stack, right? The energy loss through the stack is directly proportional to the amount of gas flow that you put through. The second problem that you have, of course, is that the capacity of your flue gas cleaning system is under stress. If you overload your your bag house or your electric precipitator with too much gas, you're pushing too many particulate emissions into your stack. And thirdly, you all know that at the end of it all, you have a monstrous or two monstrous ID fans that push out the gas flow to the stack, and they're basically sucking it out of the boiler, pushing it to the stack. And those ID fans are also running at a rating that is above their normal rating. And they are large electricity drains. You lose a lot of money and electricity on these ID fans. Where is the gas coming from? Well, the gas can come from the inlet side because your your fuel and air distribution is not ideal, so therefore you need too much excess air to do your combustion correctly. The result of that, of course, is higher loss in the boiler. The result can also be too much NOx because you have too much excess air, so the emissions are a big issue. But another big problem that you have, and I've seen this in boilers in India, in Korea, in Japan, in everywhere, in Indonesia, the other big problem is that you have ingress air into your boiler. All your pressures in your boiler and your flue gas ducts are slightly negative. And no boiler and no flue gas duct is completely airtight or gas tight. But it's a problem that you can see, and also you can see that you have a non-symmetrical gas flow, so the left side is higher than the right-hand side. These are slight biases that cause huge effect. So just give you an example. This is a typical example of a generator boiler load. You can see here the boiler load and the generator load in green and red. And you can see as a blue line, typical ID fan flow. The blue line lies exactly on the boiler load. So it is directly proportional to the flow of the gas. But this tells you exactly how much gas your boiler is putting out. And I've seen no online measurement of this ever that was working correctly with delta P or whatever. I think our measurement, our visual measurement, the first time that people can really do this. Oops, what's that? Oh. Okay, go back to this one. Sorry. You can see this as a typical example, and the last slide here that I have is a typical bias between the gas air heater outlet and the ID fan inlet. And here you can see there is a bias between these two lines. And this bias is showing you that you have ingress air between the air heater outlet and the ID fan inlet. And this bias costs you a lot of money. So it is very worthwhile to check the gas flow out of your boiler. Best location would be on the ID fan inlet. So you can directly see how much gas is pulled out of your boiler system. And that gives you a very good control over how much gas is getting into the boiler, but also how much gas is pulled as ingress air into the flue gas ducts. We've done several projects where customers were very interested in that. For example, some of the customers really would like to know where on the fan curve is my ID fan operating currently, right? You don't know that. In your DCS system, you have a diagram where you can see the ID fan, and you can pull up in your DCS screen a typical fan curve of that fan, and you see on which point the fan is operating. I'm telling you, this point that you are getting indicated most probably is incorrect, because the fan has its own internal flow measurement, which usually is a delta P measurement, and it's not working correctly. It's an ID fan. You have dusty gas going to the ID fan, even if it's after the precipitator, still enough dust in it, and the measurement is wrong. We have seen so many ID fans that are not correct, and we are pretty sure if you have an ID fan indication of flow, most of the time it's incorrect. It's drifting, like all the other are also drifting. So if you would like to know how much gas is going through your complete system. Do a digital measurement with Promicon. In this case, we don't put 2 sensors into your ID fan inlet, but it might be 6 pairs or 8 pairs. So we have a grid measurement and have a very accurate reading of what goes into your ID fan. And this is not only the end of the boiler, that's also the end of my presentation. That's pretty much what we can offer in terms of gas flow management. I can only tell you one thing: do not take gas and airflow easily. If you are asking yourself why your boiler is underperforming, I tell you 60-70% will be gas flow issues. And that's the first thing you should fix, and it's an easy fix, because once you have accurate measurement on the inlet side, your DCS system will automatically take care of the rest. So here, a better measurement means immediately a better control and a better combustion. Thank you for your attention. If you have any questions, I'll be happy to take them.
Thank you, Hans. That does conclude our formal presentation. We did have questions that came in, and we'll address them in the time we have remaining. If we don't get to your question, rest assured that we'll be providing written responses shortly. The first question has to do with airflow measurement with a different fuel. Would the airflow measurement behave the same if there is a mix of biomass pellet blended with the coal?
Answer is absolutely yes. There is no impact at all of the fuel on the airflow measurement, because what we are doing is we are measuring basically the time of flight between 2 sensors, and biomass has no impact on this transit time. So here we can say absolutely no impact. We have done, by the way, airflow measurements in biomass plants, in plants with mixed flows, as well as in pure coal plants. So the answer here is 100%, no problem.
Very good. Very good. Another question on the instrumentation itself. What is the recommended interval for performing maintenance on your system, and what does this involve?
If you have a non-SIL system, so it's non-SIL, not SIL rated, not safety integrity level, just a normal system, we recommend to look at the system every major overhaul, which means physically check the instrument, any damaged cables, is the condition good, pull the sensor out, is it okay? If the sensor is dirty, it doesn't have to be cleaned. It just has to be functional. So there's actually nothing really to do. What we would recommend is visual inspection at certain intervals. If you have a safety integrity level system, then every 2 years, every 24 months, you need to do a so-called proof test. The proof test function is built into our system, and it basically consists of repowering the system. So you switch the power off, you switch the power on, and you push a button for the proof test. And then the system goes through all the check routines and everything. And if the system comes back on with a ready signal, then the proof test is fulfilled. So you just need to note it down somewhere in your laptop or in your list that you have tested the system, and that's it. So this is all you can do. The rest is pretty maintenance free. We have clients in the cement industry that don't know where their sensors are because they've never seen them. They are 10 years in service. Nobody's ever looked at them.
Very good. Understand. A general question, I think you'd address it early on, but I think in slide 29, it covers most of what we might say there. What criteria do you use to determine the plausibility of airflow measurement? It's a sort of a little open.
No, well, this is a very good question. How do we arrive at air measurement that currently in the boiler is not plausible? Two very simple tests. Test one on the mills. if you have a mill floor and you're using one type of coal for all your mills, then the mills are doing two things with this coal. They are grinding the coal down to the pulverized level, and they are drying the coal. So these are the two functions of the mill. It grinds the coal and it dries the coal. Now, as the coal is dried, something happens thermodynamically. You are putting hot air into the mill with you have a cold air damper, so you can select a certain temperature. So you're putting the hot air into the mill, and while the air is going through the mill, it cools down from, let's say, 290 degrees Celsius down to 90 degrees Celsius. And this temperature differential, of course, is a function of the evaporation enthalpy of the moisture in the coal. So what does it mean? It means if you have a certain amount of air going through your mill, it will dry the coal by cooling down. So if you now take from your DCS, for each mill, the coal feeder, the airflow, and the temperature differential over the mill, then you should be able to calculate the amount of temperature drop, or basically the amount of energy that you have to put into the coal to dry it. And this amount of energy should be similar per kilogram of coal on each mill, right? So the drying process physically is the same in every mill. So for each kilogram of coal that you dry, you should use the same amount of energy in the primary air. Now, what we see, I would say, in 70 to 80% of all power stations on the planet is that this ratio is different on every mill. And there can only be one reason. Physics must be the same in every mill. The only reason can be that either your temperature measurement is wrong, or your airflow measurement is wrong, or your coal flow measurement is wrong. And usually the culprit is the airflow measurement. You can see this, that from day to day you have changes in this. The airflow measurement is a big issue. Coal flow measurement can also be wrong, but if you, for example, have a volumetric feeder, you don't have much drift in the coal flow. It can be wrong, but it's not drifting up and down. It's fairly repeatable. Whereas the airflow can change from day to day depending on on the way that it's clocked up. So if you give us screenshots of your mill floor, we can probably send you back a small chart saying this is the evaporation enthalpy on every mill per kilogram of coal. It should be the same, but in your plant, it's all over the place. And then you can be pretty sure your airflows are not right. On secondary airflow, it's a bit different, or so far, we don't have any drying process here. But the simple thing is what I've also shown you. You make a trend, or let's say, of all your airflows. If, let's say, 20 secondary airflows. You make a trend of that over, let's say, a week. And on top of it, you put a trend of all the associated dampers. And if you see that a damper is changing position frequently, or that the dampers have a different trend than your airflows, you can be sure that you have an airflow problem there as well. So while you cannot estimate the correct airflow, you can check the plausibility of your airflows by a very simple exercise. And if you need help on that, let us know. We'll be happy to take your screenshots and show you where your airflows are wrong.
Very good. Excellent. In terms of inaccurate airflow measurement, what's the most negative impact of inaccurate airflow measurement in a power station?
Okay, let me start with the worst. Boiler explosion. And we've seen it. I mean, we've seen boiler explosion. I won't name plants now, but it's rare, but it happens. You have boiler, I call it excursions, but it's the same like an explosion. You lose your airflow. I've seen wall-fired boilers where the damper was completely shut on one burner, and the indicator in the DCS system showed 100% flow. So you can, sometimes it happens that on very badly maintained boilers, you shut down the airflows, and then you get pockets of high CO, and these pockets of high CO, of course, can explode. So that's the worst, but that's rare. Much more common is in secondary air, a bias of airflow, so so you get air impingement of flames on the opposite side of the wall, or you get eyebrows on your burners. So yeah, wrong airflow distribution will lead to high NOx and high CO at the same time. So your combustion is bad. And wrong airflow at mill level means your mill runs unstable. You have, let's say, pulsations on your fuel flow. You have coal deposit in your coal pipes because your primary airflow is simply too low. You don't transport the fuel correctly to the burner. You have wrong particle sizing because your flow through the mill and through the classifier is incorrect. These are typical mill things. And let me tell you, I've visited a plant in India where the operators were having all the mills on manual. And I've asked them, hey, guys, this is really tricky. I mean, you have 5 mills in this plant and they're all on manual. Why are you doing this? And they told me, sir, we're doing this because it makes the plant more stable. And I immediately knew what they were talking about. Since they cannot see the airflow problem, they just notice that the mill is running more stable if they go manual. And they keep all the airflows manual. And of course, it's correct, because all your delta P measurements in this plant were making the dampers swing up and down, and all the mills were unstable. So putting them on manual makes the mill more stable. Needless to say, you can only do this as long as you run constant load. As soon as you have to do load following or you have to take mills out because of renewable energy, you can't do this anymore. So load flexibility goes along with absolutely rock solid, correct airflow measurement at all times. Otherwise, you cannot use your DCS system to control load swing. So these are the negative impacts of bad airflow, and you can correct them by using a digital flow meter.
Excellent. Very good. We've reached a hard stop. We're going to have to conclude at this time. We'll be getting back to several of you who have asked about contact information and follow-up. I'll be more than happy to get back to you quickly on those, very specific to the plants that you're working in. I'd like to thank Hans Conrads for this presentation and for Promicon for providing this webinar. And thanks to all of you attendees for spending some time with us today. This presentation was produced and marketed by Webcast Experts. We're a division of Krishnan and Associates. Please keep an eye out for future events from us bringing you more information on products and services within the power generation industry. If you'd like to contact us regarding future webinars or subjects of interest to you, or to access any of our previously held webinars on demand, contact Ravi Krishnan, rk@krishnaninc.com at 1-203-257-9232, or Luke Rathel at 203-921-1800. This concludes our presentation. Thank you again, and have a good day.